Hi guys, today we'll talk about transport of gases. In that the primary gases are two, one is oxygen, another one is carbon dioxide. So we'll talk about the transport of oxygen and carbon dioxide in the blood. Coming to the oxygen transport, it is of two types. One, it is physically dissolved in the plasma, and one we have a specialized cell called as RBC. So hemoglobin. So 98% is in combination with hemoglobin, only 2% is in physical dissolved solution, that is in plasma. And coming to this dissolved form, and the dissolving nature depends upon the partial pressure of oxygen. So that is governed by a law called as Henry's law. Gas dissolved is directly proportional to the partial pressure of the gas. So let us think that the dissolved oxygen in the blood can be calculated as solubility of that gas into arterial partial pressure of oxygen. And if you take the solubility, it is 0.003 ml per mm of Hg, and the partial pressure of oxygen in arterial blood is around 95 mm Hg. So we'll get around 0.3 ml per deciliter. But considering the cardiac output of 5 liters or the blood volume of 5 liters, we can say that 15 ml per minute is transported in the dissolved form. So 15 ml per minute is transported, and this dissolved form is not solely enough for the transport of oxygen, as we almost require 250 ml per minute as our body requirement for the oxygen. So this is not solely dependent, we are not solely dependent on this physical solution, but if we give it in high pressures, the dissolved form can be increased many times, almost 300 ml per minute, so that it will be adequate for the oxygenation of the tissues. So hyperbaric oxygen can be given as a treatment. And in combination with hemoglobin, we said almost 98% is transported in combination with hemoglobin. We call that as oxyhemoglobin. And if oxygen is removed from hemoglobin, or if hemoglobin is not bound to oxygen, we call that as deoxyhemoglobin or reduced hemoglobin. And if you see the structure of hemoglobin, it is having a heme plus a polypeptide chain, and we have such a 4 hemes, and this heme contains iron plus pigment. So totally we are having 4 iron atoms. So here you can see that these 4 polypeptide chains are together called as globin, and heme is iron plus pigment. If you see here, one is alpha and another one is alpha, so alpha 2, beta 2 is the adult hemoglobin, and each polypeptide chain is having a heme which is having a iron. So you can see that we have 4 iron particles, iron atoms. So 4 iron atoms can bound to 4 oxygen molecules, that means 8 oxygen atoms. Now coming to the oxygenation, iron in the form of ferrous is only available for oxygenation. Ferric form is not, it don't accept the oxygen. So methemoglobin, where in that the iron will be in the ferric form, which doesn't bind with the oxygen. And 4 iron atoms, 4 oxygen molecules, so we'll get hemoglobin oxygenated with 8 oxygen atoms. Now coming to it is called as oxygenation, not oxidation. If it is oxidated, it will be converted from ferrous to ferric form, but it remains in the ferrous form only, even though it is bound to oxygen. So we are calling that as oxygenation. It is only oxygenation, not oxidation. And when we take the structure of the hemoglobin, deoxygenated hemoglobin will be having a form called as tense form, where it is having less affinity for oxygen. Whereas if it bonds to an oxygen molecule, the tense form slowly changes into a relaxed state called as R state. Once it converts into the R state, it has high affinity, almost 200 to 500 times the affinity for oxygen than T form. So one molecule when bound to hemoglobin, it increases that affinity of hemoglobin to furthermore oxygen molecules to form HbO8. So if partial pressure of oxygen is more, it increases oxygenation because it converts the T form to R form. If it is low, majority of the hemoglobin remains in the T state, so affinity for oxygen will be low. And coming to the oxygen carrying capacity of hemoglobin, 1 gram of hemoglobin can carry 1.34 ml of oxygen. So normally we consider 15 grams as normal. So 15 grams is 1.34 into 15, around 20.1 ml per deciliter. If we convert it into 5 liters, it will be almost 1000 ml per 5 liter. So that is the oxygenation which is more than required, which is only 250 ml per minute, but we are getting around 1000 ml per minute. And oxygen content of hemoglobin is what actually bound to hemoglobin, and oxygen capacity, it is the potential maximum ability of hemoglobin to bind to oxygen. So it is like maximum, and it is how much. So if it is bound maximally, oxygen content, oxygen capacity will be the same. Coming to, with these two entities, we can calculate saturation of oxygen, which is oxygen binding capacity by oxygen content into 100. So it is percentage saturation of oxygen. And relation of the partial pressure of oxygen with hemoglobin dissociation or association, we are plotting a curve called as oxygen hemoglobin dissociation curve. So it is a relation between partial pressure of oxygen with saturation of oxygen. If it is more, this will be more, and it is a sigmoid shaped curve. The relation is not a linear one, but it is a sigmoid shaped curve or S-shaped curve, and it has two phases. If you see here, up to 60 mmHg, the saturation is almost linear. We call that as steep phase, and after that we have a stage called as plateau. So we have two phases, plateau phase and steep phase. So coming to the steep phase, it starts from 10 mmHg of partial pressure of oxygen to 60 mmHg. So when we are increasing the partial pressure of oxygen from 10 to 60, initially there will be a rise of saturation of oxygen linearly and rapidly, and we are calling that as steep phase. So rapid increase in oxygenation. At 60 mmHg, almost 90% of hemoglobin is saturated. And what is the significance of this steep phase? The significance of the steep phase is, with little change in the partial pressure of oxygen, major saturation of hemoglobin occurs. So greater saturation with small change in partial pressure of oxygen, and that occurs at the alveolar level. And if we come back from high pressure to low pressure, let's think that we are coming from 60 to 10 back. So we are now talking about desaturation, and let us think that at the tissue level PO2 is low. Now the hemoglobin has to release that oxygen. So greater unloading of oxygen occurs with little change in partial pressure of oxygen, and that occurs at the tissue level. This is the benefit of steep phase. And why this steep phase is occurring? Because the hemoglobin is converted from tense form to R form as it is bound to oxygen. More the partial pressure, more will be the R form. So more affinity to the oxygen. And coming to the plateau phase, so from 60 to 90 mmHg or 100 mmHg, there is no much change in the saturation of hemoglobin, only 5 to 10%. Only 5 to 10% change in saturation occurs. So almost SpO2 remains constant, apparently constant. So what is the benefit of this? Let us think that you are in a high altitude or you are doing a physical exercise. You got in a hypoxia around 95 to 60 mmHg. So partial pressure of oxygen at high altitude was reduced from 95 to 60. So almost we had a change of 35 mmHg. But the saturation of oxygen only changes 5 to 10% because at 60 mmHg it is almost 90% saturated, and maximum it will be 98 mmHg saturated. So only a range of 5 to 10%. So even though the partial pressure of 30 difference is there, still there is only 5 to 10% change in the partial pressure of oxygen, and this acts as a safety factor if there occurs pathology of the lung or hypoxia. So the plateau phase is a safety factor because very less change in PO2, more change in PO2 but less change in SpO2 saturation. So this acts as a safety factor. And coming to there is a term called as P50, which is, so PO2 at which 50% saturation of hemoglobin occurs, and usually it is at 28 mmHg. And if the P50, so here you can see here at 28 mmHg, it is 50% saturated. If P50 is increased, let us think that it was around 40. So this curve is now shifted towards right, and that causes unloading of oxygen or decreased affinity of oxygen. So if P50 is increased, it indicates the curve is shifted to right, and it indicates unloading of oxygen. And if the P50 is low, you can see the curve is shifting to left. So let us think that P50 is around 20, and you can see here the curve shifted to the left. So P50 is low, the curve shifted to left indicates increased affinity of oxygen. And factors affecting the hemoglobin binding affinity with oxygen. So one is temperature, partial pressure of oxygen, hypercapnia or hypocapnia, so partial pressure of CO2, and pH. So if the curve or if the P50 shifts to the right, we call that as shift to right. If P50 shifts to left, we call that as shift to left. And this changes the slope of the steep phase. Now the right shift means decreased affinity, usually occurs in increased temperature, increased 2,3 dpg, and increased H+. And left shift usually occurs with decreased temperature, decreased 2,3 dpg, and decreased H+. And usually this left shift occurs at alveolar level, and this right shift occurs at tissue level, because at the tissue level we have less oxygen. As the tissues are metabolizing, we have more carbon dioxide. More carbon dioxide means indirectly it indicates more H+, that means decreased pH. And as the tissues are metabolically active, the temperature increases. So all these causes reduced affinity of oxygen to hemoglobin, so that oxygen will be delivered to the tissues. Now we'll talk about temperature. So if the temperature is more, that decreases the affinity of hemoglobin to oxygen. So simply shift to right. And increased H+ dissociates oxygen. So usually this increased H+ occurs when CO2 binds with H2O to form H2CO3, which will dissociate into H plus and HCO3 minus. This H plus will cause dissociation of oxygen. So this occurs in the RBC. So 0.7 mole of H plus can dissociate 1 mole of oxygen. And coming to the hypercapnia, increased carbon dioxide in the RBC will cause increased formation of carbaminohemoglobin. This carbaminohemoglobin will cause structural change in the hemoglobin, and that causes dissociation of oxygen. And all these entities, whatever that is causing unloading of oxygen or shift to the right, is called as Bohr effect. Now you can see. So if a person is metabolically active like exercise, so the temperature at the tissue increases and metabolites will cause decreased pH, and as the tissues are metabolizing, more carbon dioxide is released, and as there is hypoxia, the RBC also undergoes anaerobic glycolysis, which causes the byproduct 2,3-DPG. This 2,3-DPG also causes the release of oxygen. We'll talk about this 2,3-DPG. 2,3-diphosphoglycerate or bisphosphoglycerate. It is a metabolic intermediate during anaerobic glycolysis. So RBC don't have mitochondria, so they undergo anaerobic glycolysis, and this anaerobic glycolysis will cause the production of 2,3-DPG. And this 2,3-DPG will bind to hemoglobin in a ratio of 1:1. One oxygen molecule, 1 2,3-DPG. So if a 2,3-DPG is bound, it alters the configuration of hemoglobin, that causes the release of oxygen. And there are some factors which affect the formation of 2,3-DPG. So acidosis inhibits anaerobic glycolysis, so decreases 2,3-DPG. Fetal hemoglobin, which is having alpha 2 gamma 2, this gamma chain has less affinity for 2,3-DPG, so that fetal hemoglobin can extract the oxygen from maternal blood. So shift to left. In high altitude or in hypoxic condition, the anaerobic glycolysis increases, and that causes increased production of 2,3-DPG, which causes the unloading of oxygen. Myoglobin is a kind of hemoglobin that is present in the muscle, and it shifts the curve to left because myoglobin is having higher affinity to oxygen, so that it can extract the oxygen from the hemoglobin present in the blood to myoglobin present in the muscle. And usually it helps in the picking up of blood when you are undergoing isometric contraction, where isometric contraction causes reduction in blood flow, so hypoxia occurs. So this myoglobin picks up that oxygen which is available in the hemoglobin. And coming to the carbon monoxide, which is having 2 times more affinity than oxygen, and this carbon monoxide will form carboxyhemoglobin. Remember, carboxyhemoglobin is formed by carbon monoxide. Carbaminohemoglobin is formed by carbon dioxide. And the hypoxia with carboxyhemoglobin is called as anemic hypoxia. Even though hemoglobin is normal, but it is not available to bond oxygen, we call that as anemic hypoxia. And carboxyhemoglobin comes under anemic hypoxia. And it shifts the curve to the left. Coming to the next gas, transport of carbon dioxide. There are 3 forms carbon dioxide is transported. One is dissolved. So physical solution, again the same Henry's law. So 7% is through dissolved form, and carbamino is 23%, that means bind to the amino component of hemoglobin, and bicarbonate form. So in RBC, this carbon dioxide is converted into bicarbonate and it is transported in 70%. So dissolved 7%, carbamino 23%, and bicarbonate is 70%. Sorry for this mistake, it's formed. And the dissolved form, same, Henry's law, solubility is directly proportional to partial pressure. So it is having around 0.06 ml, almost 20 times more than oxygen, whereas oxygen is 0.003 solubility. And 0.006 into venous blood partial pressure of carbon dioxide is 46 mmHg, so we get 2.76 ml per deciliter. And the dissolved form, the CO2 dissolved doesn't convert into bicarbonate or carbonic acid because carbonic anhydrase is very low in plasma. That's why this physical form remains as physical form. It doesn't convert into carbonic acid, which dissociates into H plus or HCO3 minus. So this is not formed. That's why it remains in the dissolved form as bicarbonate. And carbonic anhydrase is the key enzyme for the formation of bicarbonate, and it is more in RBC. So CO2 in plasma enters the RBC. It bonds with water in the presence of carbonic anhydrase, forms carbonic acid, which is a weak acid, which dissociates into H plus and bicarbonate. This bicarbonate diffuses out in exchange with the chloride. We call this as chloride shift. And the H plus forms will bond to hemoglobin, which causes the dissociation of oxygen. So oxygen is released into the plasma. And this H plus is buffered by hemoglobin. So here this chloride bicarbonate exchanger is called as anion exchanger or band 3 protein. And chloride shift is also called as hamburger shift. And whatever the H plus that is formed is buffered by the hemoglobin, and this shifts the oxygen hemoglobin dissociation curve to right, and we call this as Bohr effect. And in carbamino form, it binds to the amino group NH2 group, and deoxygenated hemoglobin binds more carbon dioxide. Coming to the carbon dioxide hemoglobin dissociation curve, it is almost linear. So with the increase of partial pressure of carbon dioxide, more saturation of hemoglobin occurs. Similarly, reverse. And the benefit of this is large amounts of carbon dioxide is delivered with small changes in partial pressure of carbon dioxide. Either it is loaded or unloaded with small changes in partial pressure of carbon dioxide. And there is an effect called as Halden effect, which occurs at the alveoli level. So more oxygen will cause less affinity for carbon dioxide, and carbon dioxide is dissociated. So increased PO2 shifts the curve to right. So shifts the carbon dioxide dissociation curve to right, and that causes dissociation of CO2. We call this as Halden effect, which occur at the level of alveoli. Thank you for your patient listening. Bye.